So today we're going to start on chemical reactions. Now, chemical reactions is going to be the single largest concept in not only this unit, but often ends up being kind of the single largest concept period in this course. On the final exam last semester, reactions counted for more marks than any other single concept. Okay, so they're pretty heavy marks in terms of the skills you're going to be asked to demonstrate in this course. In order to be able to write chemical reactions properly, you've got to be able to write the formulas of chemical compounds properly from their names. You got to be able to do the drop and swap, know what the Roman numerals mean. If that stuff is still giving you trouble, then you need to come in and get some help from me, because otherwise things are going to snowball on you so fast. Okay, and this whole thing for the next week that we'll be spending on this will just be like confusion and hell on earth for you. So, okay, if you are still confused with naming, please come in and see me for some help so we can get it straightened out before it gets really frustrating for you. All right, so we got to review today are the signs of a chemical change. So what are some signs of a chemical change? If there's a chemical change going on, what's happening?
Turning into a compound?
It could be, yeah.
Rearranged or split?
Yes. Okay, according to Dalton's atomic theory, in a chemical reaction, atoms are separated, joined, or rearranged, but they're not turned into atoms of something else. So that's what happens in a chemical reaction. What are some signs that that has happened? You could get heat produced. It could get hotter. It could also get colder. Some reactions are what we call endothermic, which means the reaction actually reduces heat. Okay, what else could happen? Or some other signs. It could change color. Okay, what else? Could get bubbles. Yeah, bubbles indicate what's being produced. Gas, yeah, so we could get a gas produced. We could get a precipitate produced. There's all kinds of signs that indicate a chemical reaction has occurred, and they occur because in a chemical reaction, I'm producing new materials, not new elements, but new materials. And from our lab that we just did, all materials have unique physical properties. So if I produce a new compound, it's going to have different properties. That means it could look different, smell different, have a different state, not be soluble anymore. Okay, any number of things could happen. A prime example could be a reaction like this. All right, that 2 looks really wonky. All right, so in this chemical reaction, I have lead nitrate reacting, lead 2 nitrate, reacting with potassium iodide. And it produces lead 2 iodide and potassium nitrate. I still have all the same elements, agreed? I have lead, I have potassium, I have nitrogen, oxygen, and iodine. That didn't change, but their rearrangement happened. So, lead nitrate, okay, is an ionic compound, and it's highly soluble in water. Potassium iodide is also an ionic compound that's highly soluble in water. Both compounds are white crystalline solids. When this reaction occurs, I get these 2 new compounds. Potassium nitrate is a white crystalline solid that's highly soluble in water, so I don't really see a lot of change there. But lead 2 iodide is not soluble in water, and it's a yellow crystalline solid. So what I end up seeing when this reaction occurs is I start out with 2 clear solutions, and when I mix them together, I get a clear solution with a yellow solid on the bottom. Okay, this stuff just precipitates out. It forms this white chunky powder in the middle of the solution that eventually settles to the bottom. Right? So I've seen some of the signs of a chemical reaction when that chemical reaction occurs. I saw a color change. I went from 2 materials that were clear to a material that was opaque yellow. Okay, I went from 2 materials that were soluble to 1 that was soluble and 1 that wasn't. Okay, I see these are the signs of a chemical change. Right? If I do this, let's say I burn octane, it's the stuff that's in gasoline. Okay, that means I'm reacting it with oxygen. When I react something with oxygen, or I burn it, the products of that are carbon dioxide and water. Okay, are the physical properties of my end products at all like my starting products? Okay, this is a clear liquid. This is a gas. This is a gas. And, well, when that reaction happens, water usually comes out as steam, so it comes out in a gaseous form as well. Okay, I'm changing the physical properties because I'm producing new materials, right? So the signs of a chemical change are present because they tell me and show me that I've created new materials with new physical properties. Everybody with me there? All right. So we're going to go over 5 types of chemical reactions. Okay, so there are 5 types that we are going to go over. Okay, and we're going to learn how to identify each reaction type. They all look very different. Right? There's really no way to confuse the 5 reaction types we're going to go over. And then we're going to go over how to write them out, how to balance them. Okay? You'll notice that in this first reaction, I didn't bother to balance the second one. Okay? But in this first reaction here, I put some big numbers in. I put a 2 right here, and I put a 2 over here. The reason I did that is I need to show that I end up with the same amount of atoms that I started with. Okay, so over here, I have 1 atom of lead. And over here, I have 1 atom of lead. Here, I have 2 nitrate ions. And over here, I have 2 nitrate ions. On this side, I have 2 potassium atoms. Here I have 2 potassium atoms. Okay, here I have 2 iodine atoms, and here I have 2 iodine atoms. Okay, I have to put in big numbers in order to make sure I don't violate the law of conservation of matter. That is, I don't create any and I don't destroy any. I can't, at the end of a reaction, have more atoms than I started with. All right, everybody follow me there? Okay, so in a chemical reaction, the final products are chemically different than the starting reactants. Okay, these 2 terms here are important. In a reaction like this one, let's just say I've got this reaction here. These are my reactants. They're the things I'm reacting together. This side of the arrow are my products, because they're what's produced by the reaction. Okay, so it's important to know what the 2 sides of a chemical reaction are called. Okay, and as we talked about here, these are some of the signs of a chemical change because they indicate I have new materials that are chemically different from what I started with. New materials would also have new physical properties. Okay, questions on that idea there? Right? So in a chemical reaction, according to Dalton, atoms can be separated, they can be joined, they can be rearranged. In this case, they're being rearranged, right? But I have not created any new atoms. I still just have sodium, oxygen, hydrogen, and chlorine. Okay? But in this reaction, I change the properties quite a bit. I start out with hydrogen chloride, which is an ionic compound that contains hydrogen, which means it's an acid. And then I have this stuff, sodium hydroxide, which contains hydroxide, which is present in all bases. Everybody with me there? That's important for your properties of compounds lab, by the way. Okay. Anything that's an ionic compound that starts with H, this was in lesson 4, okay, is an acid. Anything that's an ionic compound that has OH in it is a base. Okay, so I'm mixing a strong acid and a strong base. What am I getting at the end here? What's another way to write HOH? H2O. And what's this stuff? Salt. Okay, because if I add an acid to a base, they're going to react, they're going to neutralize each other, and they're going to produce water and a salt. All acid-base reactions produce water and a salt as their final products, okay, during the neutralization process. Okay? But I'm going to have very different physical properties. I'm going from strong acid plus strong base to neutral neutral. Okay? Very much changing the physical properties here. All right, so we're going to go over the 5 types. The first and simplest type of chemical reaction is what we call a synthesis reaction. And in a synthesis reaction, I combine 2 things, usually elements, to form a single compound. All right, now just, I'm just going to delete these things here because I don't want you to get confused with what they are. Okay, so what I just deleted was just the states of matter. And when you get into like Chem 20 and 30, you have to actually write that this is a solid and this is a liquid and this is a gas. Okay, for our purposes in Science 10, that's not important. Okay, so in this reaction here, I'm going to take 2 magnesium atoms and I'm going to react them with 1 molecule of oxygen to form 2 molecules of magnesium oxide. So I'm taking an element plus an element and forming a single compound. Okay. In terms of reading a reaction, okay, understanding what a reaction means when it's written out. Okay, when I read this out, I said there's 2 atoms of magnesium and 1 molecule of oxygen. Why didn't I say there was 1 molecule of magnesium? I mean, there's 2 atoms in both cases. Why did I say in one case there was 2 atoms and in the other I said there was 1 molecule? Okay, if I write a big 2, that means there's 2 of this. Okay, so it means they're not bonded together. There's 2 separate magnesium atoms here. When I write a 2 down here, it means that this oxygen is chemically linked to that other oxygen. Okay, there's still 2 oxygen atoms, but they're together. All right, so if you see a subscript number, you're looking at something that is a molecule. Okay, so 1 or more atoms. And then here, okay, obviously this is the molecule, but there are 2 magnesium oxide molecules. Right? So if I go back here, I got to make sure I have the same amount of everything on both sides. On the reactant side, I have 2 magnesium atoms. Do I have 2 magnesium atoms over here? I do. Okay, I have 2 atoms of oxygen on this side. Do I have 2 over here? Yes, I do, because this 2 applies to the whole molecule. Okay, it's what we call balancing a reaction. So I wrote oxygen like this because oxygen is a molecule. I wrote it as O2. Why didn't I write Mg like this? Mathematically, it means the same thing. There's 2 atoms of magnesium. Right, well, magnesium just doesn't become a molecule with itself. Only some atoms become a molecule with themselves. So if you can go to your periodic table for a second. Okay, on your periodic table, there's a bit of a color code on your periodic table. Okay, and it shows a whole bunch of them in yellow. Okay, so we've got basically nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine, as well as hydrogen, are all colored yellow. These atoms, these elements, sorry, bond with themselves. They're like twins, okay? Like Siamese twins, actually, or conjoined twins, okay? Would be more, okay? They just bond with each other and stick together as a molecule. Everybody follow me on that? Okay, so they're identified on your periodic table with a slightly different color so that you know when you write a chemical equation, those ones should have a little 2 beside them when they're by themselves. Similarly, you have phosphorus in blue or phosphorus in orange? Is in blue? Okay, so this one's colored blue because phosphorus comes as a 4. Okay, it likes to hang out in groups of 4. So it's like quadruplets. Okay, so it hangs out in groups of 4. And sulfur, which is in orange. Okay, sulfur, which is in orange on your periodic table, bonds with itself in groups of 8. So if I ever see a reaction that says something reacted with sulfur, I have to write sulfur like this. That's how sulfur occurs as an element. Okay. In nature, it's this really stinky yellow powder. It smells like rotten eggs. If I see phosphorus in a reaction, like some compound reacts with phosphorus, then I write it as P4. Okay. If something's reacting with chlorine or bromine, then I write it as Cl2 or Br2. Okay. When they're by themselves, they come in these numbers, right? So those are color-coded and indicated on your periodic table. Okay. Those are what we call the molecular elements because they form molecules when they're an element. Okay. They're the only ones that do. Notice hydrogen is the only metal that does that. Okay. So anytime you get a metal by itself, it's not going to be in a pair or a group of any kind. All right, so back to synthesis here. The other example we have, okay, I've got 2 potassium atoms, okay, in this bottom example, reacting with 1 molecule of bromine. So you can see here, 2 separate atoms for the potassium, but 1 molecule containing 2 atoms for the bromine. And then as a result of that reaction, I get 2 molecules. So here would be 1 molecule of potassium bromide, and this would be the other molecule of potassium bromide. Okay. Because it's ionic, it orients like that and makes a crystalline structure. Okay, so questions on synthesis reactions. All right, so anytime you see a reaction where you have 2 elements and you only have 1 product as on the other side, that's going to be a synthesis reaction. Okay, they're easy to identify because no other reaction type starts with 2 elements. The opposite of a synthesis reaction is a decomposition reaction. If something's decomposing, it's breaking down into simpler parts or smaller parts. And that's exactly what's going on in a decomposition reaction. A compound, a single compound, is breaking down into the elements that make it up. Right? So we can do this with water. If we run, if we arc electricity through water, it will actually split the water into hydrogen gas and oxygen gas, both very volatile separately. Okay, hydrogen gas is what the Hindenburg was filled with, that big Zeppelin that blew up. Okay, it's filled with a hydrogen gas. Okay, very highly explosive. Okay, and oxygen is the thing necessary for all things to burn. This is how we make rocket fuel. Okay, we separate water into liquid hydrogen and liquid oxygen, and we put them in big tanks and use them to propel rockets into space. That's why rockets sometimes blow up, okay, because they are using 2 very volatile things together. All right, another example of a decomposition reaction is the one we have here. We have 2 molecules of nitrogen triiodide. And when it breaks down, I get 1 molecule of nitrogen and I get 3 molecules of iodine. Okay, notice that these are both from our list of special elements there on your periodic table. Okay, they're both ones that are highlighted in yellow. So when they're by themselves, they come as pairs. Okay, it'll be important, okay, to know that, or at least remember to look back on your periodic table when writing a chemical reaction. Because if you wrote this chemical reaction like this instead of writing N2, you wrote 2N, while mathematically the same thing, it isn't chemically the same thing. This is 1 molecule of nitrogen. This is 2 separate atoms of nitrogen, and nitrogen just doesn't come that way. Right? So a decomposition reaction is unique because it is the only type of reaction we will go over with only 1 reactant. Every other chemical reaction has 2 or more things on the reactant side. All right, questions on decomposition reactions? Here? That's just, they would have told me in the question, this is nitrogen triiodide. So I would have known that it's Ni3. Okay, that's just the way that this chemical compound comes. Okay, you don't have to figure out what your reactants are. The question will always tell you, your reactants are this. Okay, well watch. It's a good question. So let's have a look here. So on this side of the reaction, okay, the nitrogen atoms are in blue, right? There's 2 of them here. Okay, because there's 2 molecules of nitrogen triiodide, right? So there's 2 here. So there's 2 on this side. They're just together now. And on this side, there's how many iodines? 2 times 3 is 6. Okay, over here, there's 2, 4, 6. Okay, so there's 3 molecules of iodine. Over here, there's 2 molecules of nitrogen triiodide, but I still have 6 atoms of iodine on both sides. Okay, like if you look at the molecules here, right? There's 1, 2, 3, 4, 5, 6 iodine atoms, and there's 6 over here. Right? It's balanced. There's 2 of them here. And it kind of looks like 1 atom, but there's this little split in the middle. Here? Well, it didn't need it here. It was in a compound. It can be any number when it's in a compound. It's only a 2 when it's by itself. Yeah? Does that make more sense? Sorry, I missed what you were getting at there. All right. So yeah, those special elements on your periodic table only have those numbers when they are alone. If they are in a compound, they could be whatever number is necessary. Okay, whatever number a swap and drop tells you it should be, or prefixes tell you it should be. Okay. Our next type of chemical reaction is combustion. And combustion reactions are probably the trickiest ones because they have a whole bunch of special rules that govern how they operate. Okay? All combustion reactions are the same in that they involve burning a hydrocarbon, that is a chemical that contains carbon and hydrogen, in the presence of oxygen. Okay? So they will always start with some carbon hydrogen containing compound. Okay? They'll be reacting with oxygen, and they always produce the same 2 products. Any combustion reaction will always produce carbon dioxide gas and water. Okay? This is why sometimes when it's really cold outside, you pull up behind another car at a stoplight and you see water dripping out of the back. Okay, that's because water is produced by the burning of gasoline, carbon dioxide and water. Okay, so we sometimes see that some of the water that condenses in the exhaust system as it's on its way out drips out the back of the tailpipe. Okay? Most of the time it comes out as steam. Okay? And if it's a warm day, we don't see it. Right? But sometimes we'll see bits of it that are condensed along the way, and we'll see them dripping out the back. Okay, a campfire, That's an example of a combustion reaction. Okay, water vapor is produced when you burn firewood. Okay, you don't see the water because it's in steam, in the form of steam. Okay, that's the big part of smoke. Right? If you see like the power plants there in South Calgary, when they're running, it looks like there's all this smoke going up in the air. Most of that is steam. Okay, most of the big cloud you see coming out the top stack of a power plant is actually steam. Okay? Yes, there's carbon dioxide in there too, but most of what you see is steam. That's why you see more of it when it's cold. Okay? In the summertime, we don't see anything coming out of those stacks. Not because they're not running. Okay? It's just because it's warm enough that the water stays as a vapor and doesn't condense. All right. With combustion reactions, there are some special rules that go along with combustion reactions. Okay? So you're going to need to write these because they're not in the notes. Okay? They have to do with balancing the combustion reactions. Okay? And we haven't talked about balancing yet, but it's going to make sense in a minute when I show you what I mean. Okay? The first rule in balancing a combustion reaction is that we balance it in alphabetical order. Okay, that is, I balance carbon first, then hydrogen, and then oxygen. Okay, always in that order. Okay. And the second rule is what I refer to as the rule of two. If you like Star Wars, that's where I got that reference from. The Sith. Always two there are, a master and an apprentice. If you don't get that, you need to get out from under the rock you live under and watch Star Wars, except for the last one because it sucked. Okay. Now, for the second rule, okay, the rule is that we start balancing with a 2 if there's an even number of carbons. And I'll show you what that means in a minute. And right now that's going to seem like Greek, but that's okay. Okay, so we're going to start with this reaction here. It's the same one that was up top. And I have C3H8 reacting with oxygen, and that's going to produce carbon dioxide and water. Okay? This reaction is what goes on in your barbecue if you have a propane barbecue. Okay? C3H8 is propane. On this side of the reaction, how many carbons do I have? 3, right? There's just a 3 here. There's no number in front of this, so there's only 3 carbons. So I want to balance alphabetically, starting with carbon. There's 3 carbons on this side, so I'm going to have to put a 3 right here to make sure I have 3 carbons on the other side. Okay? Why don't I do this? Why would I not put a little 3 there? Why do I put a big 3 here and not a little 3 there? If I put a little 3 here, is this still carbon dioxide? No, I change the molecule if I put this here. I don't want to do that. I want to change the number of carbon dioxide molecules, not change the molecule. Okay, everyone follow? So I can only add big numbers. All right, so now I've balanced my carbons. I have 3 on both sides. The next thing alphabetically is hydrogen. There are 8 hydrogens on this side. How many hydrogens are over here? 2. So what do I need to put in front of this in order to make 8? 4, right? 4 times 2 will be 8, right? These numbers that we're putting in are called coefficients. It means we multiply whatever's behind them by them. Okay. All right, my carbons are balanced, my hydrogens are balanced. Now I need to balance my oxygens. On this side, there are 2. over here, there are how many? Well, there's how many right here? 6 plus how many more? 4. Okay, there's 4 more here, right? 4 times 2 is 8. There's 8 hydrogens, but 4 times 1 is 4. Okay, so there are 10 oxygens on this side. So what needs to go in front of this to make 10? 5. Now I've balanced the whole reaction. Okay, that's how balancing works. We go back and forth, making sure that we have the same number of things on both sides. Okay, combustion ones are the hardest to balance because we have to follow all these special rules. The other ones are much simpler. Okay. All right, so that reaction did not involve using the rule of 2. Okay, but this one will. All right. Combustion reactions look a lot alike. The products are always the same. The products are always carbon dioxide and water. So if I'm following my rules here, okay, the rule is balance the carbons first. All right, so if I forget about the rule of 2, I'm going to take this 4, I'm going to put a 4 here to make sure I have 4 carbons on both sides. I'm going to take the 10 here and make sure I have 10 over here by putting a 5 there. So now my carbons and hydrogens are balanced. On this side, I have 4 times 2 is 8 oxygens plus 5 more for a total of 13. What times 2 will give me 13? 6.5. Can I have 6.5 molecules of something? No. This is why we start with a 2. Okay? If I start with a 2, I eliminate a problem of having a decimal in front of something I can't have fractions of. Okay? Namely molecules and atoms. I can't have a fraction of an atom. All right? So I put a 2 here. Now I have how many carbons? 8. All right? So I go over here and make sure I have 8. I have how many hydrogens? 20. All right, so I'm going to put a 10 here because 10 times 2 is 20. All right, for my oxygens, 8 times 2 is 16 plus 10 more is 26. 13 times 2 is 26. Okay, so I have to put a 2 in front of reactions that have an even number of carbons or I'll get a decimal and I can't have a decimal. Question? Because I need to have 10 oxygens on both sides. Over here, I have 3 times 2 is 6, plus 4 more. Yeah? Okay. Now, the last 2 types of reactions we're going to go over, okay, are probably the ones that are most common. And they only involve elements and ionic compounds. They will never have a molecular compound in them. Okay, so they only involve either elements or just ionic compounds. Okay, the first type is what we call single replacement. And it's called that because one thing in the reaction is going to get replaced, okay, by something else that's in the reaction. Okay, so in this reaction, one of the ions that's in the ionic compound will get replaced. So in a single replacement reaction, we start out with an element reacting with an ionic compound. It'll always start that way. Now, the element could be a metal or a non-metal. Could be either one, but the compound will be ionic. So in this case, since the element is a metal, this metal is going to replace who? Is it going to replace the metal or the non-metal? The metal. It has to switch with what it's like. Okay, it can't replace the non-metal because then they have 2 metals together. Metals don't bond with each other. Okay, we don't have any compounds where 2 metals are together. Okay. All right, so we're going to have this situation here where copper reacts with silver nitrate. Okay, in this reaction, copper replaces the silver, and my products become silver, solid silver, the valuable stuff, okay, plus copper nitrate. Okay. So in this reaction, the metals have switched places. Okay? This reaction would be similar if it looked like this instead. So let's say I have chlorine is reacting with calcium oxide. I don't even know if that's a real reaction, but we'll say it is. Okay, so now my element is a nonmetal. So who is chlorine going to switch places with? It's going to switch places with oxygen. They have to switch with what they're like. So a nonmetal will replace a nonmetal. That means calcium's new partner is chlorine, and oxygen ends up by itself. And is oxygen one of our special elements? It is. Okay? These are things we have to remember when we're writing out a reaction. Oh, I produced this element. Is it special? Do I need to put a 2 or a 4 or an 8 beside it? Things like that. Okay, everybody all right with that? All right, looking back at this reaction here, okay, and kind of going back to the idea that we produce things with different properties. Think about what I'm producing here. I'm taking a clear solution, silver nitrate, and I'm putting a metal in it. Copper is, kind of like that rose-colored metal that wires are made out of. Okay, I put that in there, and a little while later, I have silver, solid silver, and a solution of copper nitrate. How is that going to look different than when I started? So I have a piece of like kind of orangish metal and a clear solution. But when I'm done, what's the solid inside going to look like? It's going to look like silver. And what's the solution going to look like? What color are all copper containing compounds? Blue. Okay. If you run this reaction, okay, if you have silver nitrate and you put like a penny in it, okay, or a piece of copper wire, a bunch of copper in it, okay, after a day or so, you'll come back and on that piece of copper, there will be a silverish gray plating of metal, okay, and that metal will be silver, the valuable stuff, okay, and the solution will turn blue. So over the course of many hours, you'll see the solution go from clear to blue, and you'll see the copper being replaced with silver. You can't get rich on this reaction, unfortunately, because silver nitrate is really expensive because you can do this with it, and obviously you can't end up getting ahead that way. Otherwise, I'd go right in over to the lab and grab all the silver nitrate and go home. Okay? But it doesn't work that way, unfortunately. Silver nitrate's really expensive. Okay? All right. Yeah, about the same. Yeah. So you're not getting ahead unless you steal it, right? Don't steal it. We don't have any of it anyway. Okay, because we can't afford to buy it. It's publicly funded. There's, no money in education anyway. So. All right, that type of reaction makes sense. Okay, there's lots of things to watch for in these types of reactions because you're going to get an ionic compound in them, and you're going to have to be able to drop and swap that. You could get special elements being produced that you'll have to remember to put little numbers on. Okay, these are probably the most involved or the ones that have the most things to remember. Okay, last kind of chemical reaction are what we call double replacement. They work basically the same, except it's now two ionic compounds that are undergoing a chemical reaction. In a double replacement reaction, all we do is swap the metals. Okay, the metals just switch places so they have new partners on the other side. Okay, so on this side, calcium was with chlorine, sodium was with carbonate. On the other side, calcium will be with carbonate, and sodium will be with chlorine. They just switch partners. Okay, that's all that goes on in a double replacement reaction. I just take the metals off and switch them around. Okay, so in a double replacement reaction, all I have are ionic compounds. Reactants and products are all ionic compounds. You'll know if you've done it wrong if you end up with this. Okay, if I get two metals together and two nonmetals together, I've really screwed up. Okay, because two metals together is not an ionic compound, and this, I don't even know what that is. It's nothing, it doesn't exist. Okay, so if you end up like that, you know you've swapped the wrong things. Okay, the metals are always listed first, so just switch them around and you'll have the correct compounds. Okay, is that reaction balanced? Okay, how many calcium over here? 1. Okay, this little 2 only applies to the chlorine. So there's 1 calcium here. How many calcium here? 1. Okay, there's 2 chlorines on this side. How many over here? 2, right? There's a big 2. That means everything behind there's 2 of. So there's 2 chlorines, right? There's 2 sodiums. Are there 2 sodiums over here? Yep. All right. And how many carbonates are there? 1. Carbonate is CO3. It's a polyatomic ion. There's 1 of them here. 1 carbonate or ion contains 1 carbon and 3 oxygens. Everybody follow me on that? That's a very common misunderstanding. That's why we're doing this exact one. Okay, there's 1 carbonate, and over here there's 1 carbonate. Okay, it's just as easy to look at this as a group as opposed to separate it. I could go, okay, there's 1 carbon, 3 oxygens, 3 oxygens. I could do that, but they go together, right? They stay together on both sides, so I might as well look at them as 1 unit. All right. Now, when we communicate a chemical reaction, we have to tell people a few things. First off, we have to communicate how much of everything we have. That's what those big coefficients are for, the numbers that we put in when we're balancing. Okay? In this reaction, okay, there are how many nitrogen atoms on this side? 3. How many on this side? There's still 3. Okay, there's 2 here, and there's 1 more over here. Okay, remember, this is like a mathematical equation. This is the equal sign. Okay, 2 plus 1 is 3. 3. Okay, it's equal. There's 3 on both sides. Okay, so the arrow is like an equal sign. How many oxygen atoms on this side? 3 times 2 is 6, plus 1 more is 7. Okay, it's in 2 places. I have to keep it in mind. All right, 2 times 3 is 6, plus 1 more is 7. All right, and then for the hydrogens, there's 2 here and there's 2 here. Okay, so you got to look at both sides. Each side has to be equal. The element could be in 2 different compounds. All right, here's what I want you to do. For just the first 2 for right now, I want you to identify the type of reaction that's going on, synthesis, decomp, the single or double replacement or combustion. Okay, identify what type, balance the reaction, and write it out in words. Okay, so in other words, writing the names. All right, we'll do the second one together here just so you see what it looks like. Okay, so this reaction has an element reacting with an ionic compound. What's the only kind of reaction type that starts with element and ionic compound? Single replacement. In fact, this was the example we had of a single replacement reaction. Okay, if you go back 1 page, it's the same reaction. Okay, so this is a single replacement reaction. Okay, if I'm going to write it out in words, I'm just going to write all the names. Copper plus silver nitrate gives silver plus copper nitrate. Now, does copper have more than 1 possible charge? Yes, it can be a 1 or a 2. In this case, it's copper 2. Okay, nitrate has a charge of -1, and there's 2 of them. So this has to be the copper with the 2 plus charge. Right? Remember I was saying being able to name and write the formulas is really important. We haven't even gotten to the reactions yet where I give you the reaction written out as a sentence. Okay? And then you have to write it out like this. Okay? All right, so now I've got this written out in words. Now I need to balance the whole reaction. When I'm balancing reactions other than combustion, I start with the biggest number. Okay? Whatever element or ion is present in the largest number, I start with it, because generally it works from there. Okay, so if I'm looking at this reaction here, there's 1 copper, 1 silver, 1 nitrate, 1 silver, 1 copper, 2 nitrates. Okay, so I'm going to start with that. On this side, there's 2 nitrates. I need to have 2 nitrates over here. So what do I need to do? Put a big 2 in front of it. When I do that though, how many silver does that give me now? 2. So now I got to go back over here and fix the silver. Now there's 2 over here. All right. The only thing I haven't checked now is copper. There's 1 copper here and 1 copper here, so we're good. Okay. Usually we don't write ones, but if you want to, you can. All right. So that's what I want you to do with reaction number 1. Okay. Identify the type, balance it, write it in words. So for our third one, I've got a carbon-hydrogen containing compound reacting with oxygen. And I'm producing water and carbon dioxide. What's the only kind of reaction that does that? It's a combustion reaction. All right, so I'd write after it. Okay, it's a combustion reaction. Now I need to write it out in words. So this would be, since it's a molecular compound, carbon tetrahydride. All right, it's reacting with O2, which is oxygen. And it's going to produce water. Please write water as water. Okay? Don't try to do your like dihydrogen monoxide or hydrogen hydroxide. Just write water. Water's fine. It's the only compound that we're allowed to use the common name for, right? Because you want to write salt beside NaCl. Salt is a general term meaning any ionic compound. Okay. All right. So we got water, and then we have carbon dioxide. All right. So now I've written in words and identified the type. Combustion reactions had special balancing rules. I'm supposed to balance them in alphabetical order. So start with carbon. How many carbon are here? 1. How many over here? 1. Okay. How many hydrogen here? 4. All right. So what do I need to put in front of this? A 2. Right. 2 times 2 is 4. All right. Now I can look at my oxygens. There's 2 over here, but there are 2 here and 2 more over here for a total of 4. So what do I need to put in front of this? A 2. And now I'm done. Okay. All right, the fourth one was the example for this reaction type. It is a okay. Simple decomposition. I usually just write decomp. Okay. All right, so it's a decomposition reaction. I need to write the compounds involved. Water breaking down into hydrogen and oxygen. Now, to balance the whole reaction, right, I'm supposed to start with the thing present in the highest number. Well, that's anything, right? Hydrogen's a 2, oxygen's a 2. Okay? It's hard to know really which. But if I start with hydrogen, it looks like I'm already done, so there's no point in doing that. Okay? There's 2 oxygens on this side, and there's only 1 over here. So what do I need to put in front of this? A 2. Then what has to go in front of hydrogen? A 2. And now I'm done. Okay. All right, try those 2. All right, so our next one here, I've got chlorine, which is an element, reacting with sodium iodide, which is an ionic compound, and that's going to produce iodine and sodium chloride, which is an ionic compound. So what kind of reaction is this? Single replacement, right? All right, so it's a single replacement reaction written out in words. This is chlorine plus sodium iodide gives iodine plus sodium chloride. Notice, guys, no capital letters. Okay. All right, now I've got to balance it. I'm supposed to start with the thing present in the largest number. I've got 2 things that are kind of a tie. Will it matter which one I start with? It doesn't matter. I could pick chlorine or iodine. It won't matter. They're the present in the largest number. Either one will work for a start. There's 2 chlorines right here, and there's only 1 over here. So what needs to go in front of sodium chloride? A 2. When I do that, it gives me 2 sodiums. So I got to go back over here and make sure that I have 2 sodiums. And I do. When I do that, that gives me 2 iodines. Does that work here? Yes, it does. Okay, remember I said it's always a good sign if when you write your last number, it makes the last thing work for you. Okay, that's what just happened here again. All right, how many people are done the next one? All right, I'll give you a couple more minutes before I do that one then. Okay, let's look at the next one. So I've got calcium chloride, which is an ionic compound, sodium carbonate, which is an ionic compound, calcium carbonate, and sodium chloride. So there's 4 ionic compounds in this reaction. What kind of reaction is that?
It's a
Double replacement, right. Okay, so in a double replacement reaction, okay, there's no special balancing rules, right? We're just going to write that this is Dr, and then I'm going to write out the names, calcium chloride plus sodium carbonate. Okay, gives calcium carbonate plus sodium chloride. Now I need to balance it. What should I start with? Yep, I can start with sodium or chlorine. It won't matter which one I start with. They're both 2s. Okay, so there's 2 chlorines over here, and there's how many here? Just 1. So what needs to go here? A 2. All right, when I do that, that makes the sodium work because there's 2 over here. There's 1 carbonate right here. There's 1 carbonate there. 1 calcium, 1 calcium. All I had to do was put in 1 number, and this thing was balanced. Okay, try the last one. Okay, so for our last one, what kind of reaction are we looking at? Also a double replacement rate. All 4 compounds are ionic. Now, you might look at water and say, well, Coder, the other day you said water's molecular. Again, if there's a rule, water's the exception to it. Water usually behaves like a molecular compound, but we can write it as an ionic one. Hydrogen hydroxide. Sometimes it does behave ionically. Right? So in this one here, we're going to have hydrogen chloride. Okay, it's going to react with potassium hydroxide. To produce water and potassium chloride. Okay. Do I have to balance it? No, it's already balanced, right? If you don't see any small numbers, like any of those kind of subscript numbers, everything's a 1. Right? In a reaction where there aren't any of those, you don't have to look very hard, and it's easy to balance. Okay? Everything is just a 1. All right, tomorrow's Thursday, so you will have a quiz. Okay? It'll post at 3:30. I've already got it scheduled to post. It's going to be on naming and solubility. All right, you're going to have to tell me whether certain compounds are soluble or not using your solubility chart on the back of your periodic table. All right, so have a look over that tonight. Okay, make sure you know how to do it. Also remember, your lab report is due when we come back, okay, from the week off, so make sure you're working on that. Don't leave it for the night before.
I had a question